Today we begin Ochem 2, which is pretty exciting because we get into mechanisms and epoxides, which is kind of weird. But for starters, we're going to start with an IUPAC question. So we're given this question, right? We have to figure out what the name of this compound is. Well, obviously you want to start with drawing a picture. So we have a CH3, a carbon, another carbon, a carbon, and another carbon. Okay, so I just made 1, 2, 3, 4, 5 carbons. Okay, so I did this section. That's what I did. So now after that, I kind of look at the compound again and I see what's weird. What's weird is that this carbon has an oxygen and a hydrogen, and then there's another carbon. Well, I know that this carbon wants 4 bonds. Right now it only has 2 bonds, right? Well, what happens if we have an oxygen right here with a hydrogen? Well, that explains the OH. And technically this carbon has 3 bonds because of this hydrogen, right? Okay, so that must mean that we have an alcohol on that second carbon. Then we go down 1 and we are over here. So that must mean that this carbon has a methyl group. So we're going to add our methyl group right here. Okay, we move on. We see the same scenario with the other carbon. So he must have a methyl group. Then we go down to this carbon, which is him. And what this tells me is that this carbon has 2 methyl groups attached to it. So to not confuse you, I'm going to do it in a different color. We're going to do it in pink. Okay, so there we go. That is our compound. How do we name it? Well, remember that we're in university and the most important thing to students is alcohol. So we're going to start counting at the alcohol first, right? Another way that you can think of it is you think to yourself, oh, I see an alcohol. I'm going to start there first. So we start counting the alcohol first. So we say 1, 2. Notice that I don't count this way. I don't say 1, 2, 3. No, because I want to count so that my alcohol is on the lowest number. So we're going to say 1, 2, 3, 4, 5, and 6. Right? I'm counting this carbon because again, I want to have the longest carbon chain. Now notice that my longest carbon chain is 6, and 6 gives me a hexane. Right? Hexane. Notice the A and E, that means that there is no shape. There's no hexagon, no octagon, whatever. Hexane is just a simple carbon chain, right? Okay. So automatically I can get rid of butane, pentane, pentane, and pentane because they only have 5, and this one only has 4. Okay. So therefore, A is wrong, B is wrong, C is wrong, and E is wrong. Okay, well, we technically solved our question, but I want to go into detail, right? So again, we have our substituents, right? So our substituents are kind of like children, and the whole compound is the mom or the father, the parent, right? So our parent chain has substituents, has children. So now we have to name our children. Well, we have a child on the 3rd carbon, a child on the 4th, and a child on the 5th. So we can say that we have a methyl on 3, a methyl on 4, and a methyl on 5. Therefore, we have 3, 4, 5. Now notice I have 3 things right there, right? And there's the same child, a methyl. So therefore, we can say tri, that means 3, methyl. Okay? And now we're done with the children. We have to go to the big boss, the alcohol, right? So we can say trimethyl. Where's the alcohol? Is it on the 3rd carbon? No, it's on the 2nd carbon. So we can say that this is actually a 2-all, right? So we can say trimethyl, name the parent, which is a hex, hexane, and then we can say 2-all, right? Or you can say methyl 2-hexanol, which is some people prefer that. Typically I prefer this part, but if the professor wants you to do it like this, it's fine. You just shift the 2 to the middle, and that's perfectly fine. It's just preference. So again, our compound is 3,4,5-trimethyl 2-hexanol, okay? And that means that there's an alcohol, which is an OL, on the second carbon. There are 3 methyl groups, which are these little lines right here, on carbon 3, 4, and 5. And overall, there is a 6-carbon chain, typically referred to as a hexane. Moving on, what is the correct IUPAC name for the following compound? Okay, remember that you see some alcohol, and you're going to start counting from that alcohol first, right? So which carbon am I going to count first? Am I going to count right here? 1, 2, 3. Okay, well, that's not the shortest. Why? Here's a trick. Notice that there is something on my second carbon, and there's something on my third carbon. Okay, so you can say, there's something on my second carbon, there's something on my third carbon. If you add 2 and 3 together, you get 5. Right. But what if I counted from right to left? Well, this one would be the first carbon, that would be the second carbon, and this would be the third carbon. So there's something on my first carbon, there's something on my second carbon. So what if I did that? 1, 2. If I add them together, I get 3. 1 plus 2 is 3. Now notice that 3 is a smaller number than 5. Therefore, I want to go in the red direction, meaning I want to go from right to left. All right, so that's pretty cool. So therefore, we're going to start counting from right to left. So I have a 1, 2 diol. So notice that the all means that there's an alcohol, and the di means that there are 2. Okay, and there are 3 carbons. So overall, it's going to be a propane. And if you don't remember what a methyl or methane is, an ethane or propane, the way I remember it is MEP, right? So that's kind of like a quick way that I remember it, MEP. It's 1, 2, 3. This is methane, ethane, propane. You see 3 carbons. Oh, that's a propane. Cool. So my answer choice has to have something with diol, and it has to have something with propane. Well, look at this question, or this answer choice. There's a 1, 2. That's good. Propane, and then there's a diol. And that looks pretty good to me. See, this is wrong because you don't have 4. Butane means 4, and that's incorrect. Now, isopropanol, iso typically is like a Y shape, but if you were to consider this as a Y shape, how would you name it? Right? How would you name this? And you're saying that this is like isopropanol. That doesn't make any sense to me, and it shouldn't make any sense to you either. And ethylene glycol, well, we haven't really dealt with glycols yet, so it's a safe bet to say that it's not the correct answer choice. Therefore, D has to be the correct answer choice. Right, so we have 1, 2, propane diol as our answer choice. Moving on to number 3, select the structure of a benzyl methyl ether. Okay, well, notice that we have to find an ether, and an ether is referred to as an ROR, right? So it's just an oxygen stuck between 2 carbons. These R's are really just like long carbon chains, so it's like this, just like a random amount of carbons, oxygen, and then like another random amount of carbons. That's what it means. Okay, so this whole random amount of carbon is referred to as an R group. Okay, R group. All right. Well, it's safe to say that we need an ether, obviously. So is this an ether? I would say that it is, because you have a carbon, an oxygen, and this is technically a carbon, so that is an ether. In all these answer choices, you will find an ether. But what makes it special? We have to find something that has a methyl in it. Okay, well, a methyl benzyl. If you're stuck, remember that we want 1 ether, right? Or not 1 ether, but we want 1 benzyl. So a benzyl is this guy, right? It's that guy. And how do we find it? Well, I should rephrase that. Really, a benzyl is this guy. So the way I remember it is you have your hexane, right? But he is connected via a carbon. So it should be like this. Why is that special? Well, look at this. Benzyl has a B. And the way I remember that is that B is also in bridge. And so this benzene ring has to be attached to an oxygen via a bridge, via a carbon. So it's like this, carbon and then your benzyl. Okay? So what answer choice does that correlate to? Well, it correlates to answer choice 3 because we have a benzene ring that is attached to an oxygen via a carbon bridge. Now notice that number 2 is wrong because you're missing a carbon bridge. Right here in number 2, the benzene ring is directly attached to the oxygen. That's not what we want. We want the benzene ring to be attached to a carbon bridge like this, and that carbon should be attached to an oxygen. Number 3 does that for us, right? So again, a benzyl is just a benzene ring attached to a carbon, and that carbon is kind of like linking us like a bridge to the oxygen. So therefore number 3 would be the right one. A benzene ring, carbon bridge, an oxygen, and then another carbon for it to be classified as an ether. And an ether is just a carbon, oxygen, carbon. So carbon, oxygen, carbon, this is acting as a bridge, and we're done with that. Okay, so it's just kind of like knowing what to look for and what the concept is, right? Number 4, which compound would have the highest boiling point? Well, remember that if you have alcohols, so if you have OH, and let's do that in a different color, OH is going to give a higher boiling point. So OH equals boiling point to be super high. Why? Well, remember about hydrogen bonding. So hydrogen bonding only classifies to OH, HN, HF, right? And the way you can remember that is HNOF, right? So HNOF, it's enough for you to remember it, get it? So as long as a hydrogen is directly attached to an oxygen or a nitrogen or a fluorine atom, it's going to have hydrogen bonding. And hydrogen bonding raises your boiling point significantly, right? So which compound would have the highest boiling point? Well, A is wrong because it only has carbon and hydrogens. And, well, they're going to have a low boiling point. They're not polar, right? So again, if you're looking for the highest boiling point, you want something that has a lot of polarization. You want something that has hydrogen bonding, right? So A is wrong. Also, this is 3. Okay. What about B? Well, B is polar, but it doesn't have any hydrogen bonding. It's just it's technically an ether, right? So we have CH3, CH2, an oxygen, and then CH3. So that's an ether. It's polar, but it's not the best. Why? Well, this oxygen is by itself. It doesn't have a hydrogen. So it's not going to have that much of a boiling point. So this is wrong as well. Now C looks pretty good because we have an alcohol, and that alcohol has an oxygen that is directly bonded to a hydrogen. But is there something better? What about D? Well, D is like this. So we have a lot of hydrogens and a lot of carbons right here, but it's not too good because compared to E, it only has one alcohol. E has 2 alcohols, 1 and 2. And the more alcohols you have, or the more hydrogen bonding you have, the more of a boiling point you will create. Okay, so E would be the correct answer choice simply because it has the most alcohols. If you had a compound that had like a cajillion alcohols in it, its boiling point is going to be massive, maybe like 10 million degrees Celsius, right? if you don't have any hydrogen bondings, it'll be like 1 degree Celsius, etc. So the more hydrogen bonding you have, the higher the boiling point will be. Number 5. Which alcohol would undergo acid-catalyzed dehydration most rapidly? Well, for this one, it's kind of simple, but I'm going to get into detail about why this works. But they're really asking you which would produce a tertiary carbocation. So basically, which alcohol is tertiary? This alcohol is attached to this carbon, and that carbon is attached to one carbon. That means that this one is a primary alcohol. And the trend that you need to know is that a tertiary is faster than a secondary. Actually, hold on. A tertiary is faster than a secondary, and a secondary is faster than a primary alcohol, right? Okay. Primary means that it's the slowest, so A would be wrong. What about B, which is the pink one? Well, this right here, this alcohol is attached to a primary carbon, and that carbon is attached to another carbon, right? So that means that it's a primary carbon as well. So that's wrong. The green one, well, this alcohol is attached to a carbon, and that carbon is attached to 1, 2, meaning that it's a secondary alcohol, which is pretty fast, but not the fastest. So maybe. What about D? Well, this alcohol is attached to this carbon, and that carbon is attached to 1, 2, 3, making it a tertiary alcohol. Now remember that tertiary alcohol means that it is the fastest, so speed. So tertiary is going to be the fastest to catalyze. Therefore, D would be the correct answer choice. But why is that? Well, this reaction goes by an SN1 reaction. Why? Sometimes you can use a acid like hydronium, for instance H3O+, or let me just write this like this, H3O. So look at that. I hope your winter break was great. Okay. And let's go into kind of like classifying the numbers or the charges, right? So remember that oxygen has a valence electron of 6. How many dots are around us? 2 dots. So we can say that 6 minus 2 dots is 4. Now how many bonds are around us? 1, 2, 3. So now we can say 4 minus 3 is 1. And that is a positive number. Therefore, we have a positive charge. Okay? So that's how I know that my oxygen is positively charged. That's kind of like a review if you forget. Okay? What happens here is that this is a SN1 reaction because we don't have a negative sign, we don't have any metals. Notice that there is a positive sign on the oxygen. Typically, if there's a positive sign, it means that it's weak. And weak compounds are SN1E1. Okay? But we're not adding any heat, so this is going to be an SN1 reaction. And SN1 reactions, remember, have 3 steps. 3 steps. 3 steps, okay? So the first one is that this hydrogen is going to break off and make it into a negative, or into a kind of like a neutral compound. So we will have that H plus and then a water compound. Right? Now this oxygen is negatively charged compared to this hydrogen. Therefore, he's going to want to pick up this hydrogen that was left behind. So he's going to pick him up and he's going to create something amazing. He is going to make this compound. Right? So we added a hydrogen. And since we added some positivity to this oxygen's life, it's going to become a positive oxygen. Now, whenever you have a positive oxygen, it's a great leaving group because we can create water if this bond breaks, okay? Now, where is this bond going to break? Is it going to break towards the carbon, or is it going to break towards the oxygen? It's going to break towards the oxygen. Why is that? Well, this carbon is a lot more positive than an oxygen, right? If you look at the trend, CNOF, and then you would have your chlorine, bromine, iodine, everything goes towards fluorine. So fluorine's like the most electronegative, right? Okay. So therefore, carbon is a lot less electronegative than oxygen. Therefore, our electrons is going to go towards the oxygen. And that creates a positive carbocation. Right? It creates a positive carbocation. And that positive carbocation is tertiary. And we know that tertiary carbocations are really, really stable. So again, it follows the same trend. A tertiary carbocation is more stable than a secondary and more stable than a primary. A tertiary is super favorable, and there you go. That is an SN1 reaction review and a trend review. Number 6. Which product would you expect to obtain from the following sequence of reactions? Okay, so we're given this bad boy and we're given these reagents. Now, the first thing that I notice is that we have a peroxide. So a peroxide, the formula would be R, O, O, and then another R group, right? Again, R is just like a random string of carbons and hydrogens. And the most important thing that you need to know is that they do radicals, and these radicals actually make us do anti-Markovnikov. Anti-Markovnikov. Oh, that's cute. Okay. Well, we're doing hydroboration, anti-Markovnikov, syn addition. I know it's a lot to remember that name, but I remember that name because it tells me what to expect. I'm expecting something that is anti-Markovnikov and something that is cis or syn, right? So again, syn is equal to cis. So my answer should have something that is cis, but cis to what? Well, cis to hydrogen. So for hydroboration, you should have cis to the added hydrogen. Hydrogen. Well, you understand. Okay, hydrogen. So, what do we know? Well, since this is anti-Markovnikov, I'm going to draw this out again. We need to label our hydrogens. So this carbon has how many hydrogens around it? 0. What about this carbon? Notice that I'm only focusing on the double bond. I'm not focusing on this one or that one, okay? This carbon has 1, 2 bonds, 3 bonds, right? So to make 4 bonds, I have to have an implied hydrogen. Therefore, this one has 1 hydrogen right here, okay? Okay. Well, when we do hydroboration anti-Markovnikov, I'm going to ask myself, okay, which section is going to give the added hydrogen that I'm going to put in the least amount of friends? Because anti-Markovnikov says I'm going to put my hydrogen where I have the least amount of friends, friends being hydrogen. So if I add my hydrogen here, he's going to have 1 friend. Well, that's pretty good, but what if I added my hydrogen here? Well, he's going to have 0 friends, and anti-Markovnikov says, hey, I don't want you to have any friends, right? Or the least amount of friends. So he is going to be really bad, and he's going to put him in the least amount of friend area, right? So therefore, I'm going to have a breaking of the double bond, and we're going to be adding it, right? So we're going to say this guy right here. The double bond broke, and now we added a hydrogen. Okay? Cool. So this broke, right? Making that this guy is positive. And now the boron is going to attach to this positive part, and the sodium hydroxide is going to add a hydroxide. So basically just ignore what I just said and just remember that you're going to have an alcohol right here, okay? Kind of like anti-Markovnikov. But remember that there is stereochemistry. And so frankly, you should be having kind of like some wedges and dashes. Okay, so we have some wedges and dashes. Let's kind of like do an implied one, and let's do some dashes. Who cares? But what should our answer be? Well, 1 is wrong because there are no wedges and dashes. Also, you added the alcohol on this area, which is Markovnikov. That's bad. This one added the alcohol directly on the methyl. That's kind of dumb. Bad. This one formed a double bonded oxygen, which is like an epoxide. We're not dealing with that yet in this question, so it's wrong. But what about 2 and 3? Well, number 2 looks pretty good, but our implied hydrogen is really important. Our implied hydrogen is actually trans relative to the added alcohol. And in this reaction, we're looking for syn, right? So our alcohol should be on the same side as the added hydrogen. Okay? So actually, this would be wrong right here. This is wrong. It should actually be a syn, right? So that should be a wedge or a dash. So notice that the alcohol is on the same side as the hydrogen. If you don't like thinking about this, well, just remember that don't remember, but if you don't like thinking about this, think of trans. Okay, well, this is anti-Markovnikov, so whatever I added has to be trans. Methyl is trans to alcohol. That's right. But if you think about it further, the implied hydrogen is cis to the added alcohol. Okay, so take your poison, pick whatever you want to pick, right? I personally think of cis to hydrogen. So number 3 would actually be correct because this alcohol is on the same side as the added hydrogen. Which would be the best way to carry out the following synthesis? First, let me clear out all this mess. Okay, well, I've taken the liberty to also write out the molecular formula into like a picture form for you to understand it better. But basically we're asked to create this alcohol from this compound. How do we do that? Well, I realized something, that my alcohol is primary, or it's on the very end. It's a terminal alcohol because it terminated the chain. Well, typically to do that, you have to do an anti-Markovnikov reaction. Not always, but it's very typical, okay? So I'm already thinking of a radical reaction or something with hydroboration, okay? So that's what I'm thinking. Let's do this. What if I did number 1? Well, if I added heat and HA, I would actually do a E1 reaction, right? And it would form a double bond in the center. Why? Well, HA is just a really small hydrogen. And if you're really small, you're going to prefer Zysif, right? So Zysif says that it's going to do an internal alkene because internal alkenes are really stable. But in this case, we don't want an internal alkene because how am I going to make an alcohol over here or over here? That doesn't make any sense. So number 1 is going to be wrong. And I'm not really going to get into Zysif or Hoffman because there's frankly another video on my page that you can go to and it's going to take up too much time. What about B? Well, B says that we're going to use tert-butyl potassium oxide. And one thing that you should know is that anything with T-butyl is going to do Hoffman. And I believe it was M-A-N-N, Hoffman. Who cares? So Hoffman means that it's going to form an E2 reaction because of this potassium metal. So if it's a metal, it's going to be strong. It's going to be E2 or SN2. In this case, T-butyl is so big that is going to be E2 favored. But what's important for you to know is that this bromine breaks off, and he's actually going to make a unstable terminal alkene. That's what Hofmann does. Okay? It happens in one step, and there are no carbocations. I repeat, there are no carbocations. After that, it says on step 2, we're going to do hydroboration, again, which is anti-Markovnikov. So if you're having trouble, just realize that this carbon right here is double bonded, so he has 2 hydrogens. What about this carbon? This carbon is triple bonded, 1, 2, 3. So he's going to have 1 hydrogen. So where am I going to put my added hydrogen? I'm going to put him where he has the least amount of friends. So I'm going to put him here, right? And then I'm going to put my alcohol over there. Therefore, we are going to create this guy. Actually, do better. And then alcohol, and then an added hydrogen right there. So there we go. What I basically did was I used T-butyl oxide, potassium oxide, to create an unstable Hofmann double bond on the end, the terminal. And then after that, I took out the double bond and I added an alcohol via a radical hydroboration anti-Markovnikov synaddition reaction. That's very fun to say. To be honest, it makes you sound very smart. So number 7 would be B. B would be correct. And I recommend that you play with the other answer choices to see why it's not correct. But for me, I'm going to move on because I'm spending a lot of time doing these questions. Number 8, which reaction can accomplish the following transformation in good yield? Well, if you did answer choice A, it would look like this. And remember that it goes through a carbocation because this is an SN1 reaction, right? And so they go through carbocation. So we're going to say carbocat. So our little H is going to attack, or it's going to be attacked by this very electronegative double bond. Okay. And it's going to do kind of like a Markovnikov reaction. So therefore, our added hydrogen is over here, and our positive carbocation is over there. Now, I could do carbon tunneling, which is a fancy way to say a methyl shift. So I can move a methyl to the carbocation, and that methyl, or that plus, the plus sign moved to the central carbon, thus creating a tertiary carbocation. And as you recall from number 5, a tertiary carbocation is super stable and super favorable. But that must mean that if you're working with an acid, that the hydroxyl, or the hydroxide, will attack the positive carbocation, forming this guy, which is not good, right? So you formed a tertiary alcohol. We're not trying to form a tertiary alcohol. Therefore, A is wrong because it goes through a carbocation, which allows it to do a methyl shift, which allows a formation of a tertiary alcohol. Not good. Okay, but B looks pretty good because it does oxymercuration, demercuration. And this is actually an SN2 reaction. It's actually SN2 reaction. Therefore, there is no carbocation. Okay, so what does that mean? It means that it just goes through a Markovnikov reaction and there is no rearrangement. So therefore, Markovnikov says, I'm going to have my added hydrogen to the area with the most hydrogens, right? Well, this has 2 hydrogens over here, and this has 1 hydrogen. So my added hydrogen is going to be in this area right here. Oops, sorry. It's going to be added over here. So here's my added hydrogen. And then we're going to add an alcohol right there, which looks pretty good. There was no carbocation rearrangement. We got what we wanted. B is correct. The reason why C is incorrect is because it does hydroboration, and that doesn't do any carbocation rearrangement as well, but the problem is that it does anti-Markovnikov. So it would actually add the alcohol in this area. So you would expect your alcohol to be over here, which is not correct. So C is wrong. The answer choice is B. What about D, sodium hydroxide? Well, sodium hydroxide is really good if you want to do an E2 reaction. So for instance, let's say if we're doing this in 60 degrees Celsius, well then it would actually form a double bond over here. It's not what we want. You wouldn't put in a hydroxide. You would actually take out the double bond and put it somewhere else, right? So kind of weird, but that's what happens. Select the structure of the major product formed from the following reaction. Again, this is kind of similar to question 8, but we are actually doing an H reaction, right? An acid reaction. And I kind of already showed you the answer to this, right? But if you want the mechanism, it is like this. So we have our H, oxygen, H, and hydrogen. So this breaks off. He's going to attack the hydrogen. Now this is Markovnikov favored. So our added hydrogen is going to be in the area with the least amount of friends, which is going to be here. Actually, the most amount of friends, sorry, since this is Markovnikov. So he's going to add over here, right? And then this is going to be a positive carbocation. He's going to be attracted to this positivity. He's going to do that right there. Now we have a neutral water, right? Neutral water. And he can actually come in here. Now this oxygen has a lot of bonds, but one of these hydrogens can break off, creating just the alcohol. Okay, so that's kind of like an SN1 process, and it follows Markovnikov reaction. So therefore, answer choice 3 would be the correct answer. Because since this is an acid catalyzed reaction, it follows Markovnikov reaction, it does an SN1 reaction, and therefore it goes through a positive carbocation rearrangement. Okay, so SN1, this is Mark, and can, not always, but it can rearrange if you can make a tertiary carbocation, which is like the most stable. The reaction between 1-pentanol and HBr to yield 1-bromopentane is probably what? Well, okay, so pentane, there is no pentene, there is no double bond, there is no triple bond formation. So any elimination reactions is right out the window, okay? So C and D are wrong because they have elimination reactions, and those typically make double bonds or triple bonds, so it's wrong. Epoxidation reaction, well, we're not really working with epoxides right now, so I would assume that it's wrong as well. Okay, what about A or B? Well, this comes down to drawing the actual product and reactant, right? So 1-pentanol, pentane is 5, so 1, 2, 3, 4, 5. We have an alcohol on the first carbon, and we're trying to convert it via HBr to yield 1-bromopentane. Well, 1-bromopentane is this, 1, 2, 3, 4, 5, and we have a bromine on the first right there. Okay, well, what happened? Well, this alcohol is a primary alcohol, and this bromine is primary as well. Now, SN1 or SN2? It has to be SN2. Why is that? Well, remember that SN2, they only work with primary and secondary, never tertiary. Never tertiary. However, an SN1 reaction, it always works with a tertiary or secondary. But never primary. Okay? Now, I took something from a primary alcohol. Can SN1 do that? No, because it never works with primaries. Only SN2 can take something from a primary carbon. Okay? So therefore, SN2 would be the correct answer. B. Which of the following can be used to make 2-bromobutane? Okay, well, 1, 2, 3, 4. Bromobutane. Bute is 4, so 1, 2, 3, 4. And we have something on the second carbon, and that must be the bromine, so Br. How do we make that? Okay, well, we have this guy, but if I add Br2 to it, I would have a second bromine as well. But the answer that I want only has one bromine, so A would be wrong. Okay, A is wrong. What about B? Okay, well, B says this. It says CH3, CH2, carbon. That carbon has an OH on it. And another carbon right there, plus HBr. Okay, plus HBr. What would happen here? What would happen here is kind of like a SN1 reaction, right? So this breaks off because bromine is a lot more electronegative than hydrogen. He's picked up by this oxygen. The water breaks off, forming a positive carbocation. This bromine is then attracted to this positive carbocation, thus forming this guy right here. And that would be your answer. So I went through that really quickly, but I already showed you the SN1 reaction. And if you're kind of rusty on it, I recommend that you study up on it or watch a video, right? The reason why C and D is incorrect is because, yeah, it has a HBr, but it would only break off one of these bonds. So I'm going to kind of like write it out. We have a CH3, CH2, carbon, right? And carbon with this. So notice that, yeah, it would break one of these bonds, but you would have a double bond. And we do not have an alkene in this product. There's ane, not ene. Okay, ane means that there is only single bonds. So C is wrong because it has a triple bond, and D is automatically wrong because it has a triple bond as well. Also, it would add 2 bromines, so not good. The answer choice would be B. Which of the following could be used to make 1-bromopentane? Okay, well, 1-bromopentane, that's 5, so 1, 2, 3, 4, 5. There is a bromine on the first carbon, so let's just put it over here, bromine, right? So 1, 2, 3, 4, 5. So how do we make that? Well, if we were to draw this out, we have CH3, CH2, CH2, carbon, and then another carbon. That's double bonded. Okay. So this looks pretty good, but is it? You know, I don't think it's good. I don't think it's good. Why is that? It would actually go through a Markovnikov reaction, right? So again, this would break off, but now our hydrogen has to be added somewhere. And, well, it follows a Markovnikov reaction, therefore it's going to add to the area where it has the most friends, this area. Therefore, my bromine would actually be here, making it a 2-bromopentane, which is not good. Okay, so that's wrong. But I'll just skip to the answer. So what about B? Well, B is CH3, CH2, 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 and then alcohol. And then we're adding it with PBr3. Here's a rule of thumb when you're working with these types of reagents. Well, PBr3, it's great for primary and secondary alcohols. And all it does is that it removes the alcohol and it creates a bromine on it. Okay, so let's actually do a practice problem on this one. I'm just making these up as I go. So let's do this guy. What if we had an alcohol right here and we treated it with PBr3? Well, I'm not showing you the reaction mechanism because that's really complicated, but all it does is that it takes out the alcohol and it adds a bromine. Okay, it adds a bromine. So notice that this was a secondary alcohol, okay, and it just added a bromine. What about this? Well, if you add PBr3 to it, peanut butter, right? I call it peanut butter. It would actually just take out the alcohol and add a bromine to it. That's it. Pretty simple. Now, another thing that you need to know is that if you're dealing with tertiary alcohols, you can add HX, right? So it'd be like HCl, HBr, H fluorine, whatever. It would be like this. Okay, so we have an alcohol right there. What if I'm treating it with, I don't know, maybe HBr? Well, I'm expecting this alcohol to break off and to just put a bromine. Or if you want something more general, HX, right? So instead of this Br, what if I had HX? Well, I'm expecting my X to be there, okay? Why is that? Well, it goes via what? An SN1 or SN2 reaction. It actually goes via a SN2 reaction, right? Oh, no, sorry. Actually, a SN1 reaction. My bad. So, yeah, SN1 reaction for tertiary alcohols. Okay, and you're just doing like a simple replacement. So in this case, we have a primary alcohol. Therefore, it's pretty good if I use PBr3, peanut butter, right? So I can just replace the alcohol and put a bromine. Simple as that. The reason why this doesn't work is because it does Markovnikov, and it does it completely wrong. But hopefully that little tidbit helps you out when you're doing synthesis in your work or laboratories. Number 13. What would be the major product of the following reaction sequence? Okay, so we have this weird compound, or this reactant right here, but the only thing that you need to remember is that we're adding everything you see here except for the chlorine, okay? Except for the chlorine. Why? Well, it goes back to toluene and mesylate, and, well, it's easier if you see it. So what happens here is that we have our original compound, and we have this H over here, but the H that was attached to the oxygen breaks off and it connects to the chlorine. Okay, so let's just do CH3 for just to simplify it. So I don't want you to be confused. See this one right here, positive, and we're gonna have the chlorine that's negative. Now, because this hydrogen broke off, it's gonna be attracted to this negative chlorine. So this chlorine is gonna pick them up, and what we have now is, oh, let me finish this. Let me finish it. Okay. What we have now is this. Oh, okay. So now this O is negative. He's going to be attractive to this compound right here. Okay, so he's going to go over here. And what we now have is pretty cool. You do SO2 and then kind of like a CH3 around it. So let's just do CH3O2. Usually this whole thing right here is just gonna kind of be abbreviated to ME, right? or MS, you could say. Yeah, MS. So instead of just writing it all down, we can actually do just MS. Now, the important thing that you need to know is that we retained stereochemistry. Okay, so whenever you're doing toluene or mesylate, you're just getting rid of this H, putting in whatever is in front of the halide, and then the H that we got rid of is going to pair up with this halide. It could be a bromine, chlorine, whatever. In this example, it's a chlorine. So now we formed HCl on the side, and we retain, that means we keep the stereochemistry. So over here, we had a wedge oxygen. We're still going to have a wedge OMS, okay, or wedge OTS, depending on what you're reacting with. Okay, so we retained, kept, stereo. Okay, so we had a wedge, we still keep a wedge. If we had a hash oxygen, we would have a hash OMS, okay, kept stereo. And of course, nothing else changes in the first part, so we should still have our wedge methyl. So if you're in a time crunch, you can get rid of some of the answer choices sometimes. If you look around here and this changed. If it changed, it's wrong. Let's see, this stayed the same. So all of them stayed the same. That's pretty good. Okay, so step 1 was completed. We just basically got rid of the H and put an OMS. Okay? And it kept the stereochemistry. Now, we're going to do a sodium iodide reaction in ethanol. Well, it's important for you to remember that this is a very strong, this is going to be a very strong base. Why? Because it's a metal, and sodium is a metal, so we know that it's going to be SN2 or it could be E2. But we're not having any heat, so therefore it has to be SN2. I say that it's SN2 because of the metal, okay? And it's also secondary. And now, since it's a SN2 reaction, we're now going to react it with sodium and iodide. So what do you remember about SN2 reactions? Well, SN2 reactions, they're going to have some inversion. Inversion, if it's chiral. In this case, our example is chiral, so there will be an inversion. Are we going to be inverting over here? No. Are we going to be inverting over here? Well, maybe. Okay, maybe. So here's what happens. Now, this guy right here, this bond, is going to cleave off and go towards the oxygen. Okay, it's going to go towards the oxygen. So we have this. And now we have a hydrogen and a positive carbocation. Well, not positive carbocation, it's kind of weird. But I should retract that statement. The iodine is just going to come up right here, and he's going to be attracted. He's going to go over here. Let's do that. And now notice that because it was a wedge, my iodine is going to have to go in the back. So it's going to be a hash now. It's going to be a hash. Okay? So now we have a wedge hydrogen and then a hash iodine. Okay? So there we go. That was pretty fun. What's the answer choice? Well, this will look pretty good, but the iodine is on a wedge. And I know that whenever I finish doing a methylate or a toluene reaction, I'm going to have a retention. Well, I should have retained the wedge, and then I'm going to react it again to get rid of the wedge and put a hash. So this should actually be a hash. This is wrong. Right here, they connected the iodine to the methylate, which is not correct. It's bad. That's wrong. Over here again, your iodine is in the wrong area. Okay, so your iodine should be in a hash, and then over here this is correct because your iodine is in a hash. Okay, so this would be the correct answer choice. So as a recap, what happens here is that first we do a mesylate, and whenever you do a mesylate or toluene, you're going to retain the stereochemistry. So our oxygen was on a wedge, it's going to stay a wedge. After this reaction, we move on to reaction 2, which is this sodium iodine. Well, sodium iodine is going to go through a SN2 reaction, and that is actually going to do an inversion of stereochemistry. So now our wedge oxygen is going to be replaced, and we're going to put in a hash iodine. So pretty simple, not too bad. Question 14. Now we're given this compound and we have a reactant, HBr. We have an excess, so that means that we can do this until completion. Okay, so we have HBr right here. And remember that bromine is more electronegative than hydrogen. Therefore, when this bond breaks, the electrons are going to go toward the bromine. And we create H positive and Br negative. Okay, now let's see if I can draw this correctly. We have this right here, oxygen, and then that. Okay, cool. So this bond can actually break right here. This bond can break, and we can create this. So let's count. We have 1, 2, 3, 4 carbons. So we have 1, 2, 3, 4 carbons when an oxygen. Okay, the oxygen is now negative because we have an excess of electrons. So recall that H is positive, so he's going to be attracted towards the negative oxygen. Okay, so he's going to go over here and he creates this right here. Also, because this carbon lost its electrons, it's actually going to be more positive. Okay, so he's going to be more positive because he lost that electron. The bond between the carbon and the oxygen broke. Because oxygen became negative, you're going to have something that's positive. In this case, the carbon is a positive, right? Okay, so that oxygen is going to be attracted to that hydrogen, and this bromine is going to be attracted to this carbon because he's positive. So now we have Br, and then he's going to be attracted to this carbon. So that's 1, 2, 3, 4, and then an alcohol. So already this is a possibility, okay? So that's a possibility. For sure, 3 would be correct because one of these answer choices, so 3 encapsulates these right here. So already you see that answer choice right there. So that looks pretty good. But how did they get another bromine? Well, pretty simple. In step 2, we do it again with the HBr. So HBr again, it forms H positive and Br negative. Okay. Now, this oxygen is so electronegative that it can actually take this hydrogen. Okay, so it could take this hydrogen and it could become water, right? So it could cleave off, but I'll show you. So let's see, 1, 2, 3, 4, and then water. Okay, so water, and then we have a bromine. But again, water is positive, and every time you see a positive oxygen, well, it has the potential to break off. Okay, one of the bonds that connects it to the main chain can break. Therefore, this bond right here can actually break off, and we can have water. Okay, we can have water. So we have Br, 1, 2, 3, 4, and then actually it's like this, 1, 2, 3, 4, and he's going to be more positive, right? So again, this water gained some electrons, so it became a little bit more negative. As a result, this carbon must be positive. Okay, so now we have just water floating around, and of course the bromine is going to feel obligated to go towards the positive carbon. So now finally we have Br, then 1, 2, 3, 4, and then another Br right here. Okay, so there we go. So that should be your answer. We have 1, 2, 3, 4. This is this question right here, or that answer choice, and then this guy goes over here. So it's pretty fun. Again, it kind of like a recap. Because we have HBr in excess, you can break this bond to go towards the oxygen. This oxygen becomes more negative. He's going to be attracted to this hydrogen, so he's going to pick him up, creating an alcohol. This carbon is going to be more positive, so that bromine is going to come in and take that carbon. And then you can do it again if you take out the water and then add a bromine. So it gets pretty messy, but you know, science is a messy subject. Number 15. If cis-2-butene is treated with metachlorobenzoic acid, what is the final product? So first of all, you have to know what metachlorobenzoic acid is, and it's actually pretty fun to draw. Personally, I think it's fun to draw, if I can remember it correctly. It's like this. Then we have like a kind of like a benzene ring right here. Then we have that. Skip one, boom. Then we have a carbon that's double bonded to an oxygen. That oxygen has another oxygen that has kind of like an alcohol right there. Okay, and then we have cis-2-butene. So cis-2-butene, well, but is 4, so it's cis 4 and cis-2-butene. Okay, so that must mean that there must be a hydrogen right here and a hydrogen right there. So what happens here? Well, you should know that if you have a cis compound, you're going to have a cis answer. If you have a trans compound, you're going to have a trans answer. So automatically, when I'm thinking of looking at the answer choice, my answer choice should be cis, okay? And it should kind of look like this. All you're doing is you're keeping this the same, okay? You're keeping this the same, and then you're going to add an epoxide. So an epoxide is an O that is double bonded. Well, not double bonded, but it has 2 bonds connected to it, okay? And of course, you have your H's over here, and your H's like that, okay? So your answer choice should be number 1, okay? What happens if it was trans, or if it were trans? If it were trans, it would look like this, right? But what if I wanted to treat it with metachlorobenzoic acid? Well, then I'm adding an epoxide again, but my answer should be trans. And so you're going to have your carbon skeleton like this, right? Because it's trans. But in the middle, across the double bond, you're going to add your epoxide. Right there. So it's still trans, right? And of course you have your hydrogens like that, and your hydrogens like that, okay? So it could be like number 2, right? But frankly, that would be incorrect. It would be, this is trans and that would be cis. So yeah, okay? Not too bad. If you want it to be more accurate, you could do that. It's fine. But again, the main takeaway, I'm not going to do the reaction. The reaction is really confusing, the mechanism. But the most important thing is to remember that if you have a cis compound, you're going to make it cis again. And you're just going to be adding an epoxide in the middle across the double bond. If you have a trans compound, you're going to add an epoxide in the middle, but it's still going to be trans, okay? So not bad. Just make sure you know what you're doing, okay? This is wrong right here because, well, frankly, what happened, like, why do you have 2 methyl groups on the same side, right? That doesn't make any sense. How did this hydrogen shift over here? That doesn't make any sense, okay? And then over here, why did you connect 2 methyl groups? That doesn't make any sense either. This would be trans, and this is cis. So, for 15, number 1 would be the correct answer. And they're pretty fun. Question 16. If trans-2-bromocyclohexanol is treated with sodium hydroxide, what is a major product? First, begin by drawing your trans-2-bromocyclohexanol. So, if you draw a pretty bad hexagon, I relate very deeply with you. So, we're going to say that our alcohol is on the first carbon because there is no number. So, we have a primary alcohol, or a secondary alcohol, sorry. And then we have a trans bromine on the second carbon. So because this is a wedge, we have to have a hash bromine. It's better for you to think of it as sodium hydroxide with water. Okay, so we have sodium hydroxide in water. And actually, here's something special. Now, what you need to remember, like have it tattooed or written on your forehead or something, but if you have an alcohol that's trans to halide, so OH trans to halide to X, we can actually do an epoxide, right? So more specifically, if you have an alcohol trans to the halide and treating with a base, like a nucleophile, epoxide is available. Ooh, I wrote like 3 S's, terrible. Okay, so an epoxide is possible, okay? So this is an epoxide, so that's your answer, woo! But how did we make that? And what is the reaction? Luckily for you, I have all the time in the world to show you. Pretty cool. What I like to do is that I ignore the sodium hydroxide. So I recognize that it's a strong base, but it's kind of confusing if you think of the oxygen, okay? If you think of the oxygen, it's kind of confusing. So instead of working with sodium hydroxide, I kind of ignore it, and I think of a negative hydrogen, okay? Cool. So this hydrogen is going to be attracted to this loose hydrogen. So we're going to break this guy. He's going to donate some electrons to the oxygen, making him negative, and then this hydrogen is going to take him, okay? It's going to take him. So now what we have here is that we still have a wedge oxygen that is now negative, and we still have a hash bromine. But now we have 2 cute pink hydrides, okay? We have a hydride. He's pink. He's happy, okay? Well, what happens now? How do we get rid of this bromine? Well, that's why I told you to write it with water, because water is kind of like a simple explanation of what happens, okay? Pretty simple. So what happens here is that whenever you have water, we go via an SN1 reaction, okay? We go via an SN1 reaction. Or actually, yeah, no, it'll work, good. Okay, so what happens here is that this bromine comes out, right? He forms a positive carbocation right here. Forms a positive carbocation. And we make an oxygen that's negative, positive carbocation, and notice that this is possible because the SN1 reaction, carbocations are possible to come out. Now, the water can actually come in, right? I mean, it's kind of redundant, but you can think of like the water coming in, and then since it's a good leaving group, it could come out, but frankly, you keep it like that. So the water kind of like facilitates this SN1 reaction. So now the oxygen is going to be attracted to this positive carbocation. It's going to say, hey, that looks pretty good. He's going to go and connect. Now remember that with SN1 reactions, there is an inversion of stereochemistry. Because my bromine was a hash, whatever I add next is going to be a wedge, okay? So now we have this oxygen, and he's bonded to 2 wedges, okay? So that's how you make an epoxide with a base, okay? So if you have a trans alcohol to the halide and you're reacting it with a base, you can actually make an epoxide. If they're cis, you cannot make an epoxide, because if you go through all the steps, you would actually have a let's kind of like cut this section. We would have kind of like a wedge oxygen and then a hash bond, which is like really crooked. It's not stable. Imagine building a building with popsicle sticks. You know, if they're crooked, it's going to come crumbling down, right? So it's not stable in this form. Therefore, if you have a if you have a trans relationship, it's going to be stable. It's going to be great, especially when you're reacting it with a nucleophile, aka a base. Number 17. the product of the following reaction is what? Well, again, we're going to have to draw it out. So we have this ether, right? And we have 2 methyls on this carbon, but reacting it with hydrogen and iodine. Well, of course, the iodine is more electronegative than the hydrogen, so he's going to get the electrons when the bond breaks. Thus, we form a positive hydrogen and a negative iodine. Okay, but what happens? Well, one of these bonds is going to break for the oxygen, and we have to find out which bond is going to break. Am I going to break this bond to go towards the oxygen, or am I going to break this bond to go towards the oxygen? You know, I think I'm going to break that bond right there. Why? Well, if I do this, this carbon, he's going to lose some negativity. Whenever you lose electrons, you become more positive, right? Because the oxygen is more electronegative than carbon, he's going to gain the electrons. So this oxygen becomes negative. Well, that implies that something has to be positive, right? Well, this carbon would have to be positive. And we know that a tertiary carbocation is the most stable. You see, if I broke the other bond, I would be forming a primary carbocation, which is not stable. It's not favorable. Therefore, we should have a compound that looks like this. Looks like O, connect that. So it looks really bad, but let's do that. And then we have this right here, and then a positive carbocation right there. Okay, so that happened. And of course, since this oxygen is more electronegative, he's going to want to connect to the hydrogen to make an alcohol. And then this iodine sees this positive carbocation, and he's going to be more attracted to this positive carbocation. He's going to attach. Okay, thus we will have something like, we have like this, an iodine, then see 1, 2, 3, 4, and then an alcohol right there. So let's see, what's your answer choice? So it would be 3, right? So 1, 2, 3, 4, 1, 2, 3, 4. Yep, it looks pretty good actually. Why is number 2 wrong? Well, in number 2, they actually broke this bond, which is not what you want. Okay, they connected the alcohol to this area, which is not true. It's bad. Don't do that. Over here, they just made an ether. Like, where's your iodine? How did you facilitate this, right? And here, I don't know what they did. It was just like a scrambled mess, right? So they just completely messed it up. Terrible, disgusting. But just remember that you can actually break bonds whenever you're doing halide reactions, okay? So you can open up ethers with halides, as you just saw. And you always want to break the bond that will give you the most positive carbocation. So hopefully you can put that in your pocket. Number 18. What would be the major product for the following reaction sequence? So we have a cyclohexane, and we have an epoxide, which is pretty cool. Pretty cool. But then we're going to be treating it with a base. How do I know it's a base? Well, I see the negative sign. So CH3O negative. Okay, so a negative sign just means that it's a base. Okay, so CH3OH. Pretty cool, right? So what happens here is that, well, I have to teach you some stuff. Because this is a base, because it's a base, we are going to add the base to the area with the least amount of hydrogens. Actually, to the most amount of hydrogens, sorry. So, because it's a base, it goes to area with most hydrogen. Okay, so what I'm saying is, remember Markovnikov, right? It kind of goes to the Markovnikov reaction, okay? So between this carbon and this carbon, notice that they have the bonds connected to the oxygen, I have the option of either putting my base in here or here. Where am I going to put it? Because it's a base, I'm going to put it where it's going to have the most hydrogens. So this carbon has how many hydrogens? 0. It has 0 hydrogens. But this base right here has 2 hydrogens to it. Okay? So I'm going to break that bond and I'm going to put my base there. Okay? So this bond breaks and we are going to put it over here. My hexanes are really bad, cyclohexanes, but you know, it's whatever. So this oxygen gained some electrons, so it became negative. Let's actually do that. Let's put some dots right there. Okay, so he's negative. And because this carbon lost some electrons, he's actually positive. Okay, so he's positive. Cool. So now that gives the opportunity to this compound right here to react. Since he's negative, he's going to be attracted to this positive area. Okay, so he's going to be attracted to this positive area. Thus, we form this compound. Okay, and oxygen, and now we have this guy, which is going to be OCH3. So OCH3 right there. But remember that this oxygen is still negative, and we don't like to have negative oxygens because it's very unstable. That's why they're doing an H3O+. H3O+, or any type of acid, will give you a hydrogen on the oxygen, so it makes an alcohol. This is referred to as an acid workup. Okay, so the reaction is not complicated. All that happens is that you have an H, O, H, and then another H. This H breaks off, the oxygen connects to it, and it forms an alcohol. So now this is what you have. Right there. And then, of course, we would have the OCH3. That's it. So the answer choice should actually be 1. 1 should be the answer choice. But Brian, what happens if we're not working with the base? What happens if we're working with an acid, right? So for instance, what if I had like this acid over here, right? Well, instead of going Markovnikov, it's actually going to go to the anti-Markovnikov, okay? So instead of attacking this carbon, the acid is going to attack this carbon, okay? So it's kind of like the reverse. If acid, we will go to least hydrogen area, right? To the least hydrogens. So it's kind of like anti-Mark, okay? And this is actually going to be Mark. So you can like take a screenshot of that or whatever, but if it's a base, it's going to be better, right? B is for better, so it's going to go to Mark. But if it's an acid, A is for attack. So he's really going to try to attack the area with the least amount of hydrogens. So it's kind of like anti-Markovnikov reaction. Also, if they wanted you to quiz, you on this, the base reaction would actually be the more favorable in this question because we actually formed a tertiary alcohol, which is super stable, super good, super reactive, really good. If you were to do the acid reaction on this compound, it wouldn't be so good because you would be creating a primary alcohol, which is not that stable to begin with. And that concludes the very first video of this class. I hope you had a lot of fun. I hope that you understood most of what I was saying. If you don't, I recommend reading the book or finding practice problems on the internet and working them out. Of course, I hope that you have a great day and that you do well on this course. All right? So take care and have a great day. Thank you for watching.